Welcome back, guys. Today I am going to discuss another important section on inorganic chemistry, that is cation analysis and flame test. So you will be asked several questions in your part C essay, question number 8 or 9 about these analysis questions. So basically, when you are talking about analysis, you have cation analysis and anion analysis along with flame test, which metals give different colors. So in this particular video I am going to explain about cation analysis and anion analysis. So when you are testing for a cation, normally cations are not present as it's alone, so you have a cation mixture. That is how you analyze. You need to know how to analyze a cation mixture. So according to my picture, you can see we have a cation mixture. So then I am going to add a little bit different chemicals. Then I am going to precipitate out and identify several cations present in there. Now you need to understand this cation analysis method is a type of a gravimetric qualitative method. That means you precipitate out the cations and you separately try to identify which cation is present. And normally we have 5 groups here, and we are going to precipitate out different cations here. Now before we are going to test for these cations, you need to understand the cation mixture should not contain some anions like carbonates, phosphates, oxalates, because if those anions are present in there, our cations might already reacted with these anions and from the precipitates. So you need to have a nice mixture which is not a semi-solid or a precipitate that is formed. So now here I have indicated some anions like nitrate, nitrite, then formate and acetate. So if you have these anions in the mixture, there is no problem with your cation analysis, because these anions will not have any precipitates with the cations. So normally these compounds are soluble, right? So we will go through the group 1 analysis. So if you have a cation mixture, so we add little bit of diluted HCl, little amounts, then you have 3 precipitates that is formed: AgCl, PbCl2 and Hg2Cl2. Hg2Cl2, not HgCl2. Okay, this is Hg2 plus. So this cation some people get confused with. This is mercurous Hg2 plus, not mercuric Hg2 plus, not that Hg2 plus. Now we have 3 precipitates here. Now why we are adding little amount of HCl? Now if you add excess HCl or little bit of conc HCl, what will happen here is AgCl2 and PbCl2 will be get dissolved, forming their relevant complexes, right? So there will be no precipitates there. Then you cannot compare the analysis for group 1, right? So you cannot think whether it consists with Ag plus or Pb2 plus. We don't know, because you have added conc HCl or excess HCl. You are thinking that the precipitate should form, but it doesn't. So you might have a wrong conclusion that this cation mixture does not have silver or Pb2 plus. So in that case you are wrong there. So we add little amount. And in the case of Hg2Cl2, there is no problem if you add excess HCl, because mercurous chloride complexes are really unstable, so it will not dissolve actually, right? And further information about this PbCl2, it is nice white color precipitate, and what will happen is if you heat that means hot conditions, it will dissolve, and when it cools again, that means you allow to cool at room temperature, the precipitate reappears. So it is another nice method to identify this. This can be PbCl2. Yeah, so then you can have some specific tests for lead or either silver or either Hg2 plus, right? So think about that. Now normally when you get these precipitate, now all these 3 precipitates, those are white, so exactly we don't know which precipitate is there. Then you need to test for other specific test that is present for cation. So you need to know what are the precipitate that is formed in group 1. Now what we do is we filter this precipitate, and we have the filtrate. Now consider about the filtrate. Now filtrate is acidic. Why? This filtrate is acidic because in the first group analysis we added HCl. So this HCl is already present in the solution. So this solution is acidic. Now what we do is we bubble H2S gas. Now remember about H2S gas. H2S gas is acidic and you are trying to bubble this, and when you bubble this there will be basically 9 precipitates form. Right? How much? 9 precipitates forms. So I have written a small statement. Look at that. Precipitates with small Ksp values get precipitated. Now if you want to know about Ksp values, now you need to know about equilibrium chemistry, right? So I will just explain a little bit more about these Ksp values. What is Ksp and why we are using Ksp here. Now before trying to understand about Ksp, you need to know what is an equilibrium, right? So we will think about a reversible chemical reaction that is happening. So initially you know that for a reversible chemical reaction there will be a lot of reactants. Then these reactants will form products. That is, we normally say the forward reaction. And this forward reaction normally happens with a certain rate. But when the products are formed, now we have some products to be reacted with each other and form again the reactants using the backward reaction. So there is a forward reaction going on, there is a backward reaction going on. At some cases, at constant temperature and certain conditions are allowed, this rate of this forward reaction, the speed of this forward reaction and speed of the backward reaction can be equal, right? So in that case you need to understand the concentration of the reactants as well as the concentration of the products will not change because now it is in equilibrium. So if I want to explain furthermore, we will get a small bus. So we will say from the front door people are coming in and from the back door people are going out. Now initially the bus does not have anything, so we will say that people coming, lot of people coming. So this is like the forward reaction, right? Then there will be few people in the bus. Now from the back door few people comes out. So this is like the backward reaction, right? But at some conditions you know that the bus can have maximum about 54 people, right? So we will say we have 54 people here and another person comes and he cannot enter until another person going out from the back door, right? So this is the rate which is equal now. The forward rate is equal to backward rate. One comes, one goes. One comes, one goes. And at this condition you know that the pupil number within the bus will not change. It is 54 because one comes, one goes means the number will not change. Now chemical reactions are also like that. Reversible chemical reactions comes to equilibrium like that. And when the forward reaction and the backward reaction comes to a same rate, we say that particular reaction is in equilibrium. For an example, if one molecule reacts with another molecule to form another molecule as product, now this molecule should form the reactants. That is the forward reaction rate and backward reaction rate coming to equilibrium, right? Now in this particular situation we can define a equilibrium constant, right? It is called equilibrium constant. So what we do is normally to define equilibrium constant, we get the concentration of the products raised to its stoichiometric power and multiply each other divided by the concentration of the reactant raised to its stoichiometric power. So that is a normal definition. So we have different equilibrium constant. Now in this case we use Ksp, that is called the solubility product. Now solubility product means, now think about this precipitate that I have given here, that is HgS, mercuric sulfide. Now if you have a cation which have mercury 2 plus in your solution and if you add little amount of sulfide, so do you think that this precipitate will form automatically? So have you think about that? You have a G2 plus and you add little bit of sulfide. So do you think that precipitate will form? So you need to know there is a limitation for that. Something going to have happen there to form the precipitation. Otherwise, there will not be forming any precipitation. So you might have heard about the unsaturated and saturated solutions, right? Unsaturated solution means there will be a lot of chemicals, that mean HGS, that you can dissolve. And when you are dissolving and dissolving and dissolving, there will be a situation where you cannot further add and dissolve. That means now we have telling this solution is become saturated, right? Now anything that you are adding excess now, those will be precipitated out, right? That means you can understand the minimum need to have this precipitate is the saturated solution, right? The solution should be saturated. Additional amount is get precipitated. So the solution is saturated when a partially insoluble salt like HGS is dissolving, giving Hg2 plus and S2 minus. So HGS solid is dissolving, giving Hg2 plus and S2 minus. Now this particular reaction is a reversible equilibrium reaction. So at a certain condition, you can write this equilibrium constant Ksp as Hg2 plus concentration time S2 minus concentration. And you know that at equilibrium these two concentrations are constant, right? Then you get the product of this concentration. If stoichiometry is there, you use that as power and you write down the equilibrium constant, that is Ksp. And remember, we write this Ksp solubility product constant for 1 mole of substance at 25 degrees Celsius and in aqueous solution, that means in water. So these are book values, right? You get 1 mole, you dissolve it, you find the concentration, you multiply it and see what is the Ksp value, right? So it contains a certain book value. For an example, we will say Hg2 plus concentration is 2 into 10 to the power minus 4. And sulfide, it is 2 into 10 to the power minus 4. So what is the product? So it will be 4 into 10 to the power minus 8. So that is the book value for 1 mole of HGS, right? Now consider you have a Hg solution, Hg2 plus solution with 1 into 10 to the power minus 4. And you are adding little bit of sulfide and your concentration is 1 into 10 to the power minus 4. Then you multiply this Hg2 plus concentration and sulfide concentration, that is 1 into 10 to the power minus 4, 1 into 10 to the power minus 4, so it will be 1 into 10 to the power minus 8, which is not more than 4 into 10 to the power minus 8. That is the book value Ksp. So you know that this ionic product, we say ionic product 1 into 10 to the power minus 4, 1 into 10 to the power minus 4, this ionic product did not exceed the book value for Ksp. Book value for Ksp is for 1 mole. That is the minimum concentration or the ionic product that should need to precipitate out. Now if you add little bit further sulfide, now your concentration of sulfide is 4 into 10 to the power minus 4. So now you know that Hg2 plus 1 into 10 to the power minus 4, sulfide 4 into 10 to the power minus 4. Now the product is 4 into 10 to the power minus 8. Now this equals the Ksp value for HGS, that is the book value. Now this solution is saturated. So any amount that you are adding additionally will be precipitating out now. So that is the condition for Ksp. So try to understand that, right? So here I have mentioned with precipitates with small Ksp values. Here because in group 2 analysis I told you this H plus is there. That means the solution is acidic. And when you give out H2S gas, now according to the equilibrium reaction that I have drawn there, H2S is also in a reversible equilibrium, so it is acidic gas. It releases H plus to the medium. Now in this medium there is already high amount of H plus. So this, according to this equilibrium, the backward reaction is favored. You can see I have indicated that shifting of the reaction using a purple color arrow. And when this backward reaction is favored, the temperature or the other conditions, if they are constant, the sulfide concentration reduces. So if you have a low sulfide concentration and you have a high concentration of your cation, right, some cations might not combine with sulfide. That means when you multiply the concentration of these two, that ionic product might not exceed the Ksp values. So you can think about that and tell, if in group 2 some precipitates are coming, those precipitates should have low Ksp values, because a precipitate, the ionic product, if that increases more than the Ksp value, then the precipitate is formed, right? So in that case, you need to understand that in this particular group 2, the precipitate, if precipitates are formed, those precipitates should have smaller Ksp values, because in this particular solution, since it is acidic, your sulfide concentration is very low. That is the case, right? So we will come to the precipitates here. So I have given the types of precipitates that it can form. So HGS, CUS, Bi2S3, PBS. So all these are black in color. Then we have 3 yellow precipitates, and we have antimony, that is SB, not SB, these are like SB, orange, and we have yellow brown SNS. So I have another small writing there, AS2S5. Now why I have written that AS2S5 is AS2S3, it is arsenic 3 plus, AS2S5 is arsenic 5 plus. So 5 plus is also very important, because you need to understand here, for this particular acidic condition, I have just added H2S bubble. But if you add very fast H2S to the solution before AS2S3 precipitation, AS2S5 might get precipitated. That is one important condition, right? Before AS2S3, AS2S5 can precipitate out. It is also a yellow color solid precipitate. Now if you add slowly, like the group 2 analysis, what will normally happen is, if you have arsenic 5 plus, it can get reduced to arsenic 3 plus, and it will form AS2S3. That is one process that can happen. The other thing is, if you have arsenic 3 plus in the solution, it can form the arsenic AS2S3 precipitate, right? So I hope I have explained about the group 2 analysis, why small Ksp valued precipitates are formed. That is due to low concentration of sulfide. And I have written another thing that is called FES. So FES is black. So why I have written that? So this directly relates with the Ksp value. Now in this particular solution, FES is not precipitated because the concentration of Fe2 plus in the solution is not more than the enough required amount to exceed the Ksp value, book value of ferrous sulfide, FeS. So in that case, you need to understand, if you are analyzing a separate cation solution and you add a bubble H2S, and if you have a high concentration of Fe2 plus in the solution, surely this FES black will form, because according to the earlier explanation, like the HGS, that Hg has a certain concentration. In the solution, sulfide did not have much concentration. That is why the precipitate did not form. The precipitate did not exceed the Ksp value if you have a poor sulfide concentration. So when the Ksp is exceeded, the precipitate is formed, right? Now FES is also the same way. Now in this particular solution, Fe2 plus will not precipitate, but if you have high amount of Fe concentration, if you have that probability, then sometimes FES also can be precipitated out, and it is also black in color, right? Now what we do, we filter again and we come to group 3 analysis. So in group 3, what we do, first thing, we heat. So why we heat, I have included there, that is to remove H2S gas, because we are analyzing these cations. Now this is a separate step. So first we need to remove all H2S, so we heat it, and we add diluted nitric. So we add diluted nitric because if you have Fe2 plus in the solution, it will get oxidized to Fe3 plus, right? That is important for group 3 analysis. Then finally we add NH4OH and NH4Cl solution. This is a buffer, so this is a little bit acidic buffer. Little we have little bit acidic solution, so that is NH4Cl, that is weakly acidic salt, and you have weakly acidic base, that is NH4OH. And this buffer will work on the high pH, that means pH greater than normally 7. So this is a basic buffer, so this is in basic medium. And again I have written that precipitates with low Ksp, right? So we have 3 precipitates, that is ferric, chromic, and aluminium hydroxide, which is a white gelatinous precipitate. So again think about that, why low molecular weight, why low Ksp value, that means precipitates with low Ksp. Think about the solution, that I have given another equilibrium reaction of NH4OH. Now if you consider about the solution, you have NH4Cl, which is a salt, so it is completely dissociating to give an ammonium plus. So this ammonium plus will interfere the equilibrium reaction of NH4OH, right? Dissociation for NH4OH. Then for NH4OH, since you have high amount of NH4 plus, to keep this equilibrium constant at a given temperature, this backward reaction is favored and your OH minus concentration will be lower. So in that case, you need to understand again, if ferric hydroxide is to be precipitated, its Ksp value should be low. That is when Fe3 plus times OH minus concentration to the power 3 will ionic product will exceed the Ksp value and form this precipitate. That is because you have a low OH minus concentration. That is why low Ksp, right? Okay, then you have 3 precipitates. And a little bit further about the aluminium hydroxide, it is a white gelatinous precipitate. So in some questions, this highly asked about this aluminium gelatinous precipitate. Can we use this for kinetic studies? That means monitoring the time taken to form the precipitate. So if you remember your kinetics, we used to do a certain practical where we put a cross and we try to get the time taken to complete the precipitation by sulfur. So in that case we use sulfur, and in a certain question they are asking, can we use this aluminium hydroxide? So the problem with aluminium hydroxide is it is a white gelatinous precipitate, so it is difficult to monitor the time taken since its gelatinous nature. Right, so we have 3 precipitates here. You need to know all these 3 precipitates. So here the precipitates are significant. One is brown in color, one is dirty green in color, the other one is white gelatinous. So if a certain precipitate is formed, automatically you can tell which precipitate, which cation is present. Right, so moving on, we have the filtrate. Now it is basic in medium, and now we add H2S, and here precipitates with large Ksp values are precipitated. Why is that? According to the equilibrium reaction, now I have given you at the bottom, you can see now you have OH minus in the medium, and this OH minus will remove each H plus. So this equilibrium will be shifted towards the right hand side, and you will have a high concentration of H2 minus in the solution. And if you have high concentration of H2 minus, you need to understand that what is it? Now if some precipitate is formed, those precipitates should have high Ksp values, because in group 2 you had some precipitates when H2S gas is added. So in that case, that the metal did not form its relevant sulfide precipitate because the ionic product of the metal sulfide does not exceed Ksp. So if there are metal sulfides that exceed the Ksp, those precipitate will be formed. So those are the 9 precipitate that we discussed in group 2. But here group 4, this cobalt, nickel, manganese, zinc, all these cations were also present in group 2. But you added sulfide, does not form the precipitate. So why? Because in group 2 analysis, the condition is acidic, so low sulfide concentration, and the concentration of the metal times the sulfide does not exceed the minimum value. minimum KSP value, the book value. That is why they are not precipitated. But here the medium is basic. Now you have a lot of sulfide concentration. Now if you multiply the metal concentration with the sulfide concentration, it will automatically exceed the book value, KSP value, and they will get precipitated. So you need to understand these precipitates are formed in basic medium, not in acidic medium. That is very important to know. And again, here these three precipitate you can see, one is black, one is pale pink in color or very light like white in color. Then zinc sulfide is also white in color. So you need to know all this, right? Now we filter it and we go for group 5. So in group 5 we add ammonium carbonate. So you have ammonium plus from the previous case. So again we are precipitating with the low KSP value, because if you have a high amount of ammonium plus, there will be low carbonate according to its equilibrium reaction. So we have three precipitates, that is white in color, calcium carbonate, strontium carbonate, barium carbonate. And I have written magnesium carbonate because in the previous case in group 2, according to like the way Fe2 plus, if you have high concentration of magnesium 2 plus here, then carbonate will form, magnesium carbonate it will form. But in particular this solution, if you have a poor Mg2 plus concentration, then the ionic product of Mg2 plus and carbonate will not exceed the KSP value. Right, so then you need to know group 5, then you filter it. So you add little bit of ammonium phosphate to filter, to precipitate magnesium if you have there. So you can find magnesium phosphate as well. Then you filter it, and finally you get those remaining cations to flame test. Right, now flame test. How you are going to perform flame test is, you can use a platinum wire or nichrome wire, nickel and chromium alloy, and you immerse that in concrete Cl and you put that into in flame. Then anything that is present will evaporate and go out. Then we will have a salt, like we'll say sodium chloride, that is from the when sodium is dissolved in HCl, that will be blasted, for an example. So you get the salt, you keep little bit in concrete Cl and you put into the flame, and you will have different colors that I have given in this picture. Now lithium is red, strontium is crimson red, calcium brick red, sodium yellow, barium apple green, so copper is dark green, cesium is blue, violet and lilac. So lilac is for potassium, violet is for rubidium, so you need to change that one. And energy is increasing towards the right hand direction. So what is actually happening in this flame test? That is the thing that you need to know. Now normally this color emission, this can be done by both the cations, that means positive ions, as well as the atoms present. So mostly it is the reason for this color emission is not the positive ions, it is the atoms, right? Mostly it is the atoms. Now in this particular case I will explain with relation to sodium. Now what normally happen here is, you have Na plus in the salt. Now the flame, it contains a lot of electrons, right? The flame contains a lot of electrons, so it takes electrons from the flame and it will form sodium solid. Now you have sodium vapor in the flame, and now with the help of the energy, thermal energy, now this sodium, that is 3s1 from the ground state, will excite into its excited state, that is 3p1, and highly unstable excited state. Now sodium will come back to its ground state, meanwhile releasing certain radiation, and this radiation frequency is under the visible region, and it will be giving a nice lamp yellow color. So that is what the normal process happens. Now you might have heard why some positive ions will not give colors, like magnesium. You cannot see magnesium, why? So you need to know the reason. Now magnesium, yes, are they emitting any radiation? Yes, you need to give, first you need to give high energy, so it will excite to a high energy level, and when it comes back it releases radiation that is not within the visible region. That is the problem. It might be lower than the visible region. That is the reason you cannot see. So Another radiation that you can observe is within the visible region if you are seeing through the naked eye. So that's the end of this lesson. So please go through this. This is very important. I have told all the precipitates that can form, what are the conditions and why these are forming, and I have explained little thing about this flame test. So you need to know the flame colors, and furthermore in the next video I will explain you about the anion analysis and how to identify different gases. And thank you very much. So if you like this video, like it and subscribe to my channel. Thank you.